All right, so we'll continue our lesson here on oceans and climate. We'll take a look at surface currents in this lesson. When you're done with our lesson today, you should be able to identify the three factors that influence currents and also describe the cause of surface currents. Current describes the motion of water. Scientists measure the speed and directions of those currents. In other words, the velocity of the currents. The oceanic currents are driven by several factors. One of those is the rise and fall of tides, which is driven by the gravitational attraction of the sun and the moon on Earth's oceans. Tides create a current in the oceans, near the shore, and in bays and estuaries along the coast. These are called tidal currents. Tidal currents are the only type of currents that change in a very regular pattern and can be predicted for future dates. A second factor that drives ocean currents is wind. Winds drive currents that are at or near the ocean surface. These currents are generally measured in meters per second or in knots. 1 knot equals 1.15 miles per hour, in case you're wondering. Winds drive currents near coastal areas on a localized scale and in the open ocean on a global scale. If you're not sure about what causes winds, make sure you take a look at our previous lesson. A third factor that drives ocean currents is a thermohaline circulation. This is a process driven by density differences in water due to temperature, that's the thermo, and the salinity, the haline or haline, that has to do with the salts in different parts of the ocean. So currents driven by the thermohaline circulation that occurs at both deep and shallow ocean levels and also occurs at a much slower velocity than tides or surface currents. We actually have another lesson that's going to be talking about deep ocean currents. We'll talk more about the thermohaline circulation. Coastal currents are affected by local winds. Surface ocean currents, which occur on the open ocean, are driven by a complex global wind system. To understand the effects of winds on ocean currents, one first needs to understand the Coriolis effect and Ekman's spiral. If the Earth did not rotate on its axis and remain stationary, the atmosphere would only circulate between Earth's polar regions, areas of high pressure, and the equator, areas of low pressure, a simple back and forth pattern. So we would expect air to get warmed up at the equator and rise, and then sink at the poles, and then come back to the equator and have that kind of loop repeat. That's not exactly what happens, though. Because the Earth does rotate, circulating air is actually deflected. Instead of circulating in a straight pattern, the air deflects towards the right in the northern hemisphere and toward the left in the southern hemisphere, resulting in curved paths. This deflection is what we call the Coriolis effect, named after a French mathematician, Gustave de Coriolis, who studied the transfer of energy in rotating systems. In the northern hemisphere, warm air around the equator rises and flows north toward the pole. As the air moves away from the equator, the Coriolis effect deflects it toward the right. It cools and descends near 30 degrees north latitude. The air descending blows from the northeast to the southwest, back toward the equator. A similar pattern occurs in the southern hemisphere. These winds blow from the southeast toward the northwest and descend near 30 degrees south latitude. These prevailing winds, known as the trade winds, meet at the intertropical convergence zone, also called the doldrums. They meet between 5 degrees north and 5 degrees south latitude, where the winds are very calm. The remaining air that does not descend at 30 degrees north or south latitude, continues toward the poles and is known as westerly winds, or the westerlies. Michigan lives in the westerlies, in a westerlies latitude. The trade winds are so named because ships historically took advantage of them to aid them in their journeys between Europe and the Americas. So here we have a diagram of atmospheric circulation and the Coriolis effect, creating the global wind patterns, including the trade winds and westerlies. Low pressure here, as that air rises, that creates a low pressure, travels to the north, and then it starts sinking. That's going to create a higher pressure and kind of circle back around. These are what are called those trade winds, and then some of that air is going to continue north and deflecting. These are going to be the westerlies. Global winds drag on the water's surface, causing it to move and build up in the direction the wind is blowing. And just as the Coriolis effect deflects winds to the right in the northern hemisphere and to the left in the southern hemisphere, it also results in the deflection of major surface ocean currents to the right in the northern hemisphere, a clockwise spiral, and to the left in the southern hemisphere, counterclockwise spiral. These major spirals of ocean circulating currents are called gyres, and they occur in the north, and they occur both north and south of the equator. They do not occur at the equator, though, where the Coriolis effect is not present.